Okay. Hello, Kris. Can you hear me?
Yes, I can hear you well.
Okay. My name is Ola, and this is the AI for Good breakout session. The team is glad to have you here, and so you can share your screen. You can let's start at this. Hello, team. You can say hello in the chat window.
Okay, so I'm going to share my screen in a sec.
Okay.
I'm also going to be asking people to edit this document throughout the talk. So just for reference, you can check it out there. Okay, so I'll get started then. It sounds good.
Yeah.
And
okay.
Yeah, anybody, if you have questions or anything at any point, this is pretty informal, right? I think I'm happy to just discuss things as well. So I'll start with the talk, but don't hesitate to just start asking a general question too.
Okay, Kris, that works. We're open to that, and we're looking forward to this.
Okay, so I'm sharing the screen now. Okay. Do you see my slides?
Yes, Kris. It's on the screen.
Okay, so it's great. Yeah, my name is Kris Sankaran. I'm an assistant professor at the University of Wisconsin-Madison. I recently finished my postdoc at Mila in Montreal. Thank you for the invitation to speak. I'm also, I hope everyone is doing well. I know I was kind of very surprised when all of a sudden they had to reschedule the bootcamp. But I hope everyone is taking care. Yeah, right now is a very unusual time everywhere. Okay, so I'm going to be telling you about AI, sustainability, and climate change. If you want access to these talks, I believe they've already been posted and shared. You can also just find them online at this link. Okay, so getting into the content. So from a very high level, think about technology, right? Kind of for a long time, whenever people thought about technology, what it was really used for, it was to transcend physical limitations that people have, right? So kind of the classical beginning of the Industrial Revolution example I always think about is this Manchester to Liverpool line. So 200 years ago almost, that was the first railway that was built. And it all of a sudden made it possible to travel distances okay. Sorry about that. Yeah, it was much faster than anything you could walk. It was way faster than anything by horse. There's a story about Queen Victoria taking one of these trains and then asking the conductor to drive it a little bit slower because he couldn't enjoy the scenery in the same way that when you were taking a carriage, right? So for a long time, technology has been about physical limitations. But relatively recently, maybe in the last few decades, a lot of technology is now around information, right? And the limits that people have, it's no longer how quickly can you run, it's how quickly can you lead, right? Or how quickly can you make decisions based on information that's coming in, right? And these kind of limits are becoming very apparent when we generate more and more data, right? So here's a statistic that I recently learned that I thought is, it kind of indicates the scale of this issue, right? So in 2021, they estimate that the amount of bandwidth, so amount of internet connection going back and forth across countries is going to exceed 1900 terabits per second. So that's 46 million sets of this book. This is complete works of Shakespeare, and that's every single second, right? So to be able to manage this sort of flow, people need different kinds of tools. Okay, and just a high-level philosophical point I would like to mention. I'm going to be talking about AI for social good and climate change, right? I think both around AI and around climate change, there's a lot of discussion around, or a lot of kind of thinking that's, to me, sounds like a belief in things being inevitable, right? Either AI or climate change. People think like, well, it's going to happen, you know, there's nothing you can really do about it, right? And that's a kind of resignation that I want to challenge you to think beyond. The tools that people create can really shape how things develop, right? I mean, example I always to think about is like the ancient Roman road system, right? These weren't things that just automatically appeared. They were things that were deliberately created, and they had a lot of influence on the way the world was created. Here's a picture of all the closing power plants and opening power plants, right? So it shows that there is still many decisions where people have control, right? And thinking deliberately about what are the consequences of choices that people make and the ways these tools can amplify those intents. That's what I want you to be thinking about throughout this lecture. Okay, so how is this going to work? In the very beginning, I'm going to give a discussion about some useful conceptual ideas. So I'm going to draw into a little bit of history of science, and I'm going to discuss some kind of principles for AI for good. Then I'm going to draw from this survey paper that I really like about computational sustainability. And then finally, I'm going to discuss some connections between climate change and machine learning. And that is kind of my area of most personal interest. Okay. So let's talk about amplification. Okay. So there are certain kinds of technologies that people like to call packaged interventions, right? So the idea of a packaged intervention is you build some technology and then you're able to just package it up and then mail it over to whoever is going to be able to benefit from this technology. And then it just somehow magically improves things as soon as you receive the package, right? So the canonical example of this is a vaccine, right? Because you, like, as soon as you just get the vaccine, then you're immune, right? Things are, it's such an easy technological fix, right? But it turns out that this attitude is not very helpful for most AI for good kinds of projects. And I'll explain a little bit why here. So I don't know if people have heard of this kind of project. This used to be very, very popular maybe 10 years ago. You would hear about it in the news all the time. But there was a project called One Laptop per Child. The promise was it was going to deliver a laptop to people for $100, right? So this would make it accessible to huge populations. It was especially, people were trying it a lot in India, right? But then it turned out to not really have that much of an effect. When people went in and actually did controlled trials and studies looking at changes in educational attainment, then having this laptop didn't actually make that much of a difference in those results. So the question is kind of what happened, right? And in retrospect, it sounds silly, and it sounds silly that people didn't think about it. But then the natural thing happened is people got the laptops and they mostly used it for games, right? And I think the issue is deeper than just saying, oh, well, you should make sure that they always use it for educational things. Like that's not a sufficient response for why this didn't work, right? The real reason this didn't work is that this was a packaged intervention, right? It was just deliver the technology and then just hope it would just make everything better. But it's not enough to just deliver technology and then increase people's educational attainment, right? It's not like a vaccine, right? Here's another example of this sort of thing. So what if the full power and vividness of something, which I'm going to ask you to guess, teaching were to be used to help the schools develop a country's new educational pattern? What if the full persuasive and instructional power of this thing I'm going to ask you to guess, were to be used in support of community development and the modernization of farming. So anyone want to guess what X is? You can type it in the chat maybe.
Okay, Kris is asking us to guess what X is. You can reply in the chat window.
Okay, I see.
Okay, Kris Sadiq says AI. I'm waiting for the next person. Please send it to everyone, not just the panelists.
AI is a good guess, but not quite.
Okay. Somebody still thinks it's artificial intelligence. More answers. Guess X.
I'll give a hint. It's much older.
Okay. Okay, Kris. There are more answers. Virtual reality.
Okay. What? How do I see actually? Okay. I actually can't see all the answers for some reason. Maybe it's because I'm sharing screen.
Okay. Okay. So let me just read out the answers. Someone says technology, virtual reality, behavioral science, data science, AI, machine learning, data science. Someone says IoT, mathematics, technology. Okay. STEM.
Okay. No, this is pretty good. I will now reveal. No one has gotten it yet, but the answer is TV. So and if you think from at that time, like, wow, we're all of a sudden going to be able to see we're going to be able to record people and movement, and there's going to be so much possible, right? But that's just not how people use TV, right? It turns out like access is not enough. This is kind of the recurring theme here, right? And this is kind of the central point about packaged interventions and technology a little bit more generally, is that what people get out of technology depends on what they can do and what they want to do even without technology, right? So the reason that one laptop per child didn't just magically improve people's educational attainment was because you need to somehow nurture that talent, and you need to kind of amplify the intents that people already have for learning, rather than just expect some sort of additive effect, right? So technology affects the costs of doing things, but then the intent is key, right? That's kind of the same thing with television, right? As an educational medium, television is very powerful, but it can amplify all sorts of intents as well, right? And I would argue that the same is true with AI and data science and a lot of the other answers that people shared. Okay, so this is a very useful conceptual framing for thinking about AI for good. Okay, so what are some other corollaries of this theory? So one, inequalities can be exacerbated, right? Because if it really is an amplifier, then the people who are already not able to benefit much, right? So they kind of think about what people can do and what want to do. So if they already cannot do much, and technology is likely not going to help much more, versus the people who already are very kind of in very good situation, then they're going to be able to benefit the most as others. It explains package interventions, why they don't just work. Like, it's not enough to just deliver something and then expect something magical to happen. And then final is that a local success need not scale, right? Because things are so context dependent. Since in one context, people might be able to use technology to amplify a very clearly described intent, versus in another context, the exact same technology might not be used to the same success. Okay, so this is kind of a point about implementation. Okay, so that was like the first philosophical kind of idea. And yeah, now I'm going to move on to automation and augmentation. Here's kind of the final little history lesson before we dive into examples. Okay, here's a story that I like. Before computers. So I don't know if people know about Gaspard du Prony. He was a early 1800s, late 1700s mathematician. And what he organized was this compilation of these big mathematical tables. So back in the day, before calculators, if you wanted to be able to evaluate certain functions, right? If you wanted to evaluate the log, or especially like more complicated functions, you would look it up in a table, right? You would say, my X value is this, you would look in the table where it is, and then you'd find that value, right? And compiling these tables is a lot of effort, right? It used to be a mostly individual effort, but what du Prony realized was that you could apply the idea of division of labor to mathematics, right? So this was just around the Industrial Revolution, right? So everyone was starting to think about how can you take a big complicated task and how can you break it down into many small pieces, which can then be divided, right? So what he realized is that he kind of had this whole chain of command where there were these top mathematicians of the time, I think like Legendre, one of the inventors of linear regression, was one of these mathematicians, right? And he had this kind of top mathematicians of the time figure out different general approaches for compiling these tables. And then they would be kind of, math students who were very good would be working under them and dividing up like certain parts of the computation. And at the very lowest level, there were people who were doing the actual arithmetic. And a lot of the people who were doing the actual arithmetic were hairdressers, unemployed after the French Revolution, because there were no more aristocrats to fix the hair. So that was how some of these first computational tables were made. And this kind of division of labor idea was what inspired Babbage, Charles Babbage, who invented the first computing engine. So difference engine number 1 was inspired by this effort. And I think the takeaway I want you to have from this story is that what we often think of as automation, right? Like difference engine number 1 is automation, right? It is automating this laborious process of coming up with computing tables. What we often think of as automation is first preceded by a kind of a manual division of labor, right? The work of compiling these tables had been done by hand, and it had been divided up into simple enough tasks that eventually it was able to be totally replaced by a computer. So this is the very first example, right? And this is a kind of recurring theme. Yes, so kind of once these tasks become decomposed, once there's a division of labor down to these very straightforward kind of addition, subtraction kinds of things, then that's when automation becomes powerful. So general recommendation then for AI for good. Don't imagine applications out of thin air. Seek out work that people are already doing, right? You will find that there's lots of very good work being done that is mostly manual. I'll describe a lot of applications in the remainder of the talk. But as you try to think about kinds of projects that you are interested in, there's no need to invent things out of the air, right? So, obviously there's an XKCD about anything like this, and there's one about this too, right? So much of AI is just figuring out ways to offload work to random strangers, right? But the point is, once you make something really simple, that's when AI can be very powerful, because then it can scale up that work. Okay, here's another, we fast forward 150 years. This is an amazing article if you are into history of science. There's an article called As We May Think by Vannevar Bush, who was one of the very early computer researchers. And he had this idea of something called the Memex. And what the Memex is, it was this sort of kind of computerized desk, even though they didn't really have individual, personal computers at this time, right? But what this device would let you do is it would let you read information and then take notes and then store it in some sort of kind of centralized place that makes it easy for you to link pieces of information together, right? So the point would be, you'd be reading something, you would take a photo, and then that photo would get stored kind of physically. And then it would also come with kind of a ledger saying, this is how to look it up. These are kind of the keywords, right? It was kind of this incredible thought experiment where when you read it now, you think like so many of his ideas came true, right? He even had this idea of a camera that you can wear on your head. Because at the time, like a camera is like a very big object. It's not something you just carry around, right? And it's already thinking like, what if one day everyone's going to be able to take a camera, like a photo so easy, right? So a neat article to read, but an important point that he also kind of introduces is that what he's proposing is something that he calls augmentation, which is different in kind of a subtle way from automation, right? Augmentation is where you think of a computer more as a tool rather than as a complete replacement for human labor, right? So what augmentation does is it takes the limits that people have in terms of memory, so like the Memex is kind of about memory, and then it augments that ability. So you are still relying on the person to do the kind of high-level planning and intention, but then you're just making them that much more effective at the thing that they're trying to do, right? So it's increasing the power of people rather than automating tasks for people to ignore. And so it's an important distinction. Okay, so what are the sorts of things that AI can augment? I think at a high level, what AI is very powerful, it can augment sensing and it can inform action, right? Sensing because it can take these 46 million works of Shakespeare per second and it can compress it down to a human consumable form, right? There's a lot you can learn by analyzing this kind of huge data ecosystem, but there's no way you're going to be analyzing image by image or bit by bit or word by word. Right? Okay, so that's one way it can augment our ability, just navigating and compressing that information. The second way it can augment human ability is it can inform decisions, right? If you want to make these kind of, imagine hypothetical outcomes for some system, this is exactly what machine learning is very good at, right? It's able to mine through historical examples and you're able to anticipate, this is what you think the outcomes will be depending on which choice you make, right? And as a tool to support decision-making, that's a very powerful way to augment human reasoning. Yeah, so I think of augmentation and amplification as kind of dual ideas to one another, right? So augmentation is it is that quality of technology that makes people much more effective at what they try to do. But amplification is saying you can only get that much better at something if you are making that kind of deliberate effort, right? And kind of follow-up is that AI, and especially in AI for good, it's useful when it's part of some larger system, right? Rather than using the word AI for good, I would rather people used, we are working on education and we're using AI technologies, or we are working on public health or renewable energy or whatever it is that is kind of the social application, make that front and center. And then describe how people who are working in that area can be augmented by AI. That is a different framing than just saying we are doing AI for good. Right? And here's another nice article, Data for Good Lacks Precision by Sarah Hooker. it elaborates much more on this and kind of some related points. Okay, so I'm going to be getting into some examples now. I think it's a good time to maybe have a short kind of Google Doc break. So maybe is it possible people have this link? So do you see, how do I get out of this?
Hey, Kris, would you like me to share the link again, or you share it in the chat window? Okay.
Yeah, yeah, that would be great. And then maybe people can look at maybe the first 3 questions, and then feel free to answer whichever of the first 3 questions. And let's take 5 minutes, and I will pick out some of the interesting responses, and we can talk about them. Does that sound good?
Okay, that's great. I've shared the link to the Google Doc in the chat window, but we can just read and people can respond.
Okay, yeah, sounds good. And feel free also if people have questions or comments that they want to put in here, you can do.
Okay, so team, kindly check the Google link. Kris, please share your screen that shows the Google Doc.
Oh.
Yeah, so sure. Whoever is not clicking can look at the screen.
Yeah, that makes sense.
Yeah.
Yeah, let's think about these 3 questions for now.
Okay. So we can start with question 1. Okay, Kris, so we have the first answer for question 1. I don't know if it's showing on your screen yet.
I see the environment pollution.
Oh, okay.
Yeah. Feel free to answer whichever of these questions that excite you. I see a lot of people here. And I know at least one person can edit.
Okay, so if you don't have answers to question 1, you can go for question 2 or question 3. So we have an answer already for question 1. So I know you guys are online, so please answer the questions. And then you can put your answers in the chat window too. You can just put okay, Okwere, I can see renewable energy in the chat window. Is that an answer to question 1 or question 2 or question 3? Kindly indicate that. Okay, Kris, we have quite a number of answers now.
Yeah, no, I see them. This is interesting.
Okay, someone has an answer for question 4. If you're replying in the chat window, Olarewaju, there's a link in the chat window that you can click on, and then you can just collaborate live on the screen from Kris's screen. Carbon emission mitigation. Please, when you're answering the questions, you need to indicate, are you answering question 1 or question 2? Kris, we have an answer for question 4 already in the chat window. Yes.
Yeah.
Okay. Okay, we have an answer for question 1. Fire outbreak. Okay, Oluwatoba, there's a link in the chat window. Kris just added it again. You can look on the screen or click on the link, and then, you can be part of the live collaboration. So if you're just joining in, like Oluwatoba, we have a couple of questions that the team is answering. There's a link in the chat window. You can click on the link and answer any of the questions. Of course, please do not delete what other people have written. Yes, just pick your line and work.
Okay, maybe we give it 1 more minute and we get back to the main part. This is super interesting. I'm enjoying this.
Yeah. Okay, team, in case you're joining, everyone is working on a particular Google link. It's in the chat window, and they are answering questions from their perspective. So if you still want to participate, kindly click on the link. Let me share it again. So that's the link to what you can see on your screen. You can answer any of the questions. You are open. The answers are not limited. You can put your suggestions there. Okay, Olushola, because of you, I'll share the link again. Remember that you can put your responses directly in the Google link that I have shared in the chat window. Okay, this is interesting. We have quite a number of responses. Well done. Thank you for participating. Yes.
Okay. Yeah, no, I think it's a lot of cool answers. We will be getting more into the kinds of topics for 4 through 7 in the rest of the talk, so we can revisit this. I think there will be more discussion on this, and you'll have more background for that. Definitely the first couple of questions, though, I like the kinds of answers people have. I think we've covered a lot of environmental things, and just some general kind of AI ways it can be helpful. Yeah, environmental and energy, especially today. Packet interventions, interesting. You got some points about malaria and mosquito nets. So yeah, no, I think that's a very cool, or like a very good observation, right? These, to actually make a change in the world, right, it requires a much more critical lens than just delivering things, right? And we have one example of a success, is the telephone. Even though I think that's kind of also transcending a physical limitation, right? It's like you cannot shout at people in a very directed way physically. So instead we build a device that kind of amplifies our ability to communicate. But yeah, there's some great stories of how people reacted when they first, like, to the first telephone. It was at the World Exhibition, and people, it was, I think, the Emperor of Brazil was one of the first people to test out a telephone in public, and there was some interesting reactions. Okay, so we're gonna get back into the talk. So people can see my slides again.
Hello, Chris. Your screen is back up. It has the
Okay.
presentation slides now.
Okay, awesome. And actually, I can also see the chat now in the other screen. So like, if you have questions and comments, I'll be keeping an eye out there too. So let's get into computational sustainability for the developing world. This is going to be mostly based on a survey paper that has the same title. The purpose of this section is to give kind of a relatively broad set of examples about AI for good. So examples in environment, examples in health, just so that you have kind of the breadth covered from this lecture. We're going to dive a bit deeper into climate change in the last part. Okay, so first think about developing world contexts. I mean, I think this is kind of one of these big questions about AI for good, like how there are kind of whole workshops that are around how can AI support developing world contexts, right? So at first it seems like there are a lot of these big kind of challenges around limited data being used right now, right? Or kind of infrastructure that's developed in a relatively unplanned way, right? But then there's also these kind of huge opportunities, right? So first, there's a lot of people online, right? And data is always being generated whenever there are people online. And kind of second is that there are often situations where if the infrastructure had been set up kind of with everything in mind at the beginning, then in a way AI isn't necessary. Machine learning wouldn't be needed. The system would already, by design, be extremely efficient, right? But then in systems where things are growing more organically, that's when it's really important to be able to use machine learning, because that's when you need to be able to adapt to complicated and rapid changes, right? So we'll see how that can happen. Some specific kind of ways that machine learning can help in developing contexts. One is intelligence gathering. So a story. I once visited kind of an AI kind of winter school in Nepal. And there was a really interesting question that one of the professors there asked. The question was, had gone to the Minister of Health, and then the Minister of Health had just taken over, and then asked a very basic question, and no one had the answer. The question was, how many doctors are there in Nepal? And no one in the room could say anything, right? This is the Minister of Health, the person who's in charge of healthcare in the country. And there was no idea, right? There was no kind of central record of how many doctors, let alone any knowledge of the specific kind of specialties, right? So in this kind of, it seems like a thing that ought to be known, but when you think about it, it's a very complicated problem, right? The only reason it might be known in other places would be because things have been centralized a lot, right? But when things haven't been centralized in advance, then you need some way of gathering intelligence, right? And kind of as we were talking about how machine learning can augment sensing, this is one of the ways that machine learning can help in this context, right? It can augment sensing related to intelligence gathering. Okay, a second theme, so amplification, right? We've been talking all about amplification. So the point is, sometimes there are areas where there are experts, but there are just not that many of them, right? And in this situation, it becomes very important to be able to amplify their ability, right? Because in a place, if there were millions of experts around kind of being able to recognize malaria in blood, say, then you don't need a computer to help any experts out. Like there are just enough people that you can divide the labor up. But then if there's only a certain number of them, then you need to make sure that each of these subdivided tasks, you can have a single person get through many more of those tasks. And then the last point is some sort of reason is that it turned out that this was not the bottleneck, right? The bottleneck was not recognizing tuberculosis once you had a slide prepared. The bottleneck was actually getting the slide prepared properly. The issue was that they were getting a lot of these kind of healthcare extension workers to go and do this tuberculosis diagnostics. But then preparing these slides requires a lot of care, and it's actually kind of a tricky process. So you need to be trained and you need to have done enough practice to be able to prepare this slide properly. If you don't prepare the sample correctly, then it doesn't matter what technology you have, you're not going to be able to recognize whether there's tuberculosis there, right? So again, thinking carefully about what step in this pipeline you're actually trying to improve. Okay, here's a neat example. So this is actually the founder of the company that does this is, he's from Nigeria, Charles Onu. So you can read, he was a postdoc in Montreal when I was at Mila. The project was around being able to detect asphyxia from the sounds of a newborn baby crying, right? So what it did, it was like a phone app, you could record the sound, and there were enough examples of this is the sound of a cry from an asphyxiated baby, so it was like a low oxygen. And you could tell the difference just from the cry. And then it would be able to give kind of an early warning, so a way of getting an initial check before deciding like, okay, we need to definitely see a doctor for this. So this is very useful when it's otherwise very hard. Like if you know it's going to be a very hard journey, then having that sort of app can be very powerful. So yeah, you can learn about it's in the reference here. Another example, so this is now a very popular example, crop disease monitoring. So this is another amplifying experts application. So governments will hire agricultural extension workers, and what the workers will do is you look at the bottom of these, here's a cassava plant. You look at the bottom of the cassava plant and then you have to count all these whiteflies. So these whiteflies are pests that can ruin a crop, right? And usually you just count them by hand, right? So this is a very tedious kind of thing. But then if you're able to detect them automatically and you're able to count them automatically just from a picture, then that can make it much faster for the workers to get through that task and then concentrate. Extension workers are already doing. Here's a neat example around traffic. Understanding commuter behavior is very hard, actually, but it's also very important in places that experience very big traffic problems. And a lot of the worst traffic in the world right now is in urban centers that grew very, very rapidly, right? So grew rapidly without kind of centralized urban planning. The usual way of trying to understand commuting behavior is you look at call detail record data. Or sorry, the usual way is you go and do like behavior surveys, right? So you just mail all the people in your, or you go door to door and you ask people like, okay, how much did you drive last week? What times did you drive? And how much traffic were you, right? It's a very kind of laborious and not that high signal kind of process. Another thing you can do instead is something called call detailed record data. So what it is when you move around with a cell phone, it's always sending information back to a radio tower, right? And you can actually track the movement of people just from these kind of cell phone, mobile phone data, right? So you don't need to look at any calls or anything like that, but then just knowing where people's phones are, you're able to watch commutes happen just by looking at that data. And then it can highlight that there's certain areas that are bottlenecks, right? And then you can start thinking about oh, maybe we can build like auxiliary lanes, or maybe we should make that a one-way street, things like that. But it's much easier to use that kind of data than it is to do a survey. Similar process, you can just use closed circuit TVs. So here's an example from a paper by UN Global Pulse that was looking at streets in Jakarta, Indonesia. And just by looking at these images, they were able to say, okay, this is about the flow rate of different kinds of vehicles across the roads. So that can give you pretty detailed traffic information around a city without requiring very expensive or time-consuming tooling. Okay, here's a different flavored application, but I really like it because it's kind of in the spirit of kind of open, kind of democratic technology. So the tool is called Humanitarian OpenStreetMap. So what it was used for, it's originally just a purely human, no AI kind of tool. What it is you go to this website and then you just label things. You label like oh, on this coordinate on the map or at this location, there is a restaurant or a grocery store or a hospital, right? And just through the work of all these volunteers, they're able to label pretty detailed maps and keep them updated. And here's a campaign that was done before and after the 2015 Nepal earthquake of Kathmandu. And you can see just how much more detail the mapping got just from that crowdsourcing campaign, right? And so since that original campaign, people have been now using machine learning, AI, to accelerate this humanitarian OpenStreet mapping process, right? So the point is you can use satellite imagery and you're able to tell like, okay, the road should be probably around here. And then you can suggest it to the volunteer, like maybe you should just draw the road here, and then you can accept it. And then it's a much easier annotation process than drawing the boundaries of a building by hand or drawing the road out piece by piece, right? Important point though is that it's not just a matter of build a deep learning model to recognize the road and then apply that deep learning model everywhere and just use that as the result. Like that does not work. Humanitarian OpenStreetMap has a very high standard. I mean, they use it in all these relief projects, right? So you do not want to have a false positive road detection when in fact there was no road. That might keep all the supplies from being delivered, right? So it needs to be very high quality. It needs to be human vetted. But then if you can amplify the volunteers who are already building this sort of very good database, then like AI can play a very powerful role. Okay, kind of a related point. This is also using satellite imagery. So land use mapping. So land use maps, they're used a lot in conservation or urban planning, even like climate change, right? If you want to be able to recognize, are there kind of flood barriers or like floodplain barriers for cities? It's very helpful to know just what is the land around different places. In this picture, right? The green, this is forest. Purple, I think it's built environment. I'm actually not sure. But then in blue is water, right? So you can just, and the neat thing here is like there's actually a person who's clicking and making corrections to this model on the fly, right? So it's not just like you give it an image and then it just makes predictions everywhere and you use that. Instead, you use the model to speed up the process of mapping it, right? So painting it pixel by pixel is tedious, but if you use the model, it can make pretty good suggestions. And if you make corrections, then the model gets better over time. Okay, so that's computational sustainability in developing worlds. So that's just kind of very high level applications. Now I'm going to dive into climate change and AI. Okay, So first, just some of the basics of climate change. So what causes climate change? So climate change is caused by, we burn carbon, that carbon gets into the atmosphere, and then it has a greenhouse effect, right? So the earth will just start absorbing more heat, right? And that creates a warming planet, right? So that is like the physical process of climate change, or the physical process of global warming. That causes climate change. So what are some of these? When people talk about climate change, they're typically talking about the consequences of global warming, right? And the main consequences are there are going to be pretty dramatic shifts in climate patterns, right? So rising sea levels, extremes in the water cycle, right? So either very severe rainfall or no rainfall at all. And kind of as a result of these shifting climates, right? So areas that used to be Mediterranean biome will become desert biome, or places that used to be forest will become savanna. Like there's going to be a lot of shifting of biomes in that way. And that has consequences for a lot of the species. So species that are not adapted to those shifts in environment will be lost. Okay, so that is what we talk about when we talk about climate change. Now, two useful definitions. One is mitigation, other is adaptation. Mitigation is the process of reducing the amount of carbon in the atmosphere. The idea is you can mitigate future warming by trying to reduce the amount of carbon in the atmosphere. That's why when you hear about all these countries having targets for net zero carbon or negative carbon emissions, that's because they're trying to mitigate climate change. They're trying to reduce the amount of carbon. It controls the amount of warming if you can reduce the amount of carbon. Second definition is adaptation. Adaptation refers to, suppose certain things will change. How do you improve resilience, or how do you improve robustness, right? So if the certain parts of climate or an ecosystem might change, you might try to make it so that the effects that those changes have on ecosystems or on societal systems are somehow less severe. Okay, so kind of a high-level point I want to make here, just like a historical lesson about climate change. In the last decade, the way people have talked about climate change has changed a lot. I think if you look back, and the first panel, or the first government investigation that brought up climate change to central national attention in the US was in the late 80s. But then kind of throughout the early 90s, most of the talk about climate change was around, oh, yes, we need to elect politicians who will help pass laws around climate change, right? And that is still very important, right? So it's still very important that, things like the Paris Accord are happening, and that countries commit to very substantial changes in their energy systems. But then I think there's less feeling in the community that this is something that you can just leave to experts, right? I think people used to just think about, you leave it to the government or you leave it to the scientists, but there's nothing I can do, right? But now I think people very much agree, like there's a lot that individuals can do, and that kind of as a whole, right? To address this problem requires a mobilization of people from very many different backgrounds. The analogy I've heard that I really like is fighting climate change. We don't need a Manhattan Project for for fighting climate change, right? The Manhattan Project is like, you get the team of experts and they will solve it for the rest of the world, kind of thing. So rather, it's like fighting World War II entirely, right? It's like you need to mobilize the entire population. Right. Okay. So that's climate change. How does machine learning fit into this, right? So machine learning can support in many different ways, actually. I think a lot of people, their first instinct when they hear machine learning for climate change their first instinct is to think about, oh, you know, like climate models, right? Like I've heard about these things that can simulate the climate for a few decades out. Or they think about forecasting or like weather prediction. These are very important applications, right? So I think they're highlighted here. You can see the section 7 is about climate science. Forecasting is also there, right? And energy is one of these sections too, the first section, right? But there's many different ways that machine learning can help. Or improve the efficiency of a building, or kind of promote the discovery of better electrical, like better batteries or better protocols for rolling out electric vehicle fleets. These are all things that have a pretty substantial impact on climate change. And they're not just forecasting weather. Okay, so it's a very interdisciplinary, multi-domain thing. Kind of a final point. So machine learning is not a silver bullet, right? This should not be a surprise, given everything I've been talking about in the first part of this lecture. I've been kind of talking about how machine learning can augment and amplify, but it's not you cannot treat these things as packaged interventions, right? But you can look at discipline by discipline, and you can see how people currently solve a lot of problems, and you can increase the efficiencies of these systems, right? Kind of a story I've heard around climate change in energy. Kind of sometimes people think like, oh, you know, we'll solve climate change as soon as we build better solar panel, right? But it turns out that, you know, our solar panels themselves, if you go to a big solar farm, the solar panels themselves are very, very efficient. Like the chemistry and the material science doesn't really, like it can benefit from improvements, but that's probably not where you're going to get most of the benefit. What happens, the biggest problem there is actually a systems problem. Each individual solar cell is good, but when you assemble it into the solar farm, there are lots of inefficiencies in how that energy is combined, right? Or how it's harvested, right? And how then it arrives on the grid. So it's making these kind of systems more efficient. That can have as big an impact as discovering some new fundamental property, right? And what is good at making systems more efficient? Like this is exactly what machine learning is made for, right? Machine learning is able to take a very complicated system and then optimize some objective, right? So, okay. Here's a useful diagram, I think, whenever thinking about climate change. It reflects the previous slide, right? In the previous slide, I was trying to make the point that machine learning, it helps for more than just like weather forecasting or climate modeling, right? Machine learning can help a lot of areas that are relevant for climate change. Here are some of those areas, and they're being mapped to how they contribute to climate change, right? So I think just whenever you think about how much can something affect climate change, just remember this diagram, right? So like transportation is 15%, and it's going into kind of road and rail. So there's like individual personal commuting, and there's also long distance shipping, right? Electricity and heating is 30%. So buildings, right? So building here is about 15%, right? Industrial processes, another kind of major part. So yeah, kind of improving the efficiency of a building helps with climate change. Okay, so that is primer on machine learning for climate change. Let's look at some specific examples. Okay, so one, forecasting energy supply and demand. So it's really, it is making a very big difference that renewables are being incorporated into the energy grid. They've been incorporated very rapidly in the past few years, and that's a very good thing for climate change, right? The more we can have the grid powered by renewables, the better. And one of the big challenges though with the grid is again this systems problem, right? Even though each of these like renewable plants are good, an issue is that they do not provide power as consistently as a fossil fuel-based power plant, right? So if all of a sudden it's a cloudy day, or if the wind dies down a little bit, then the amount of power available will decrease, right? So the way they describe this formally is this is a variable supply problem, right? So it's not fixed constant supply like fossil fuels. But what you can do is you can try to forecast both the supply and the demand, right? You can forecast both the supply and the demand of electricity, and then you can try to adapt your generation schedule, right? So you can make sure that you can adapt the generation schedule to match this anticipated supply and anticipated demand, right? So it's forecasting with this decision-making in mind. Kind of a related problem is sometimes you can forecast demand and then give people incentives to reduce their demand during times that you think supply might be low, right? So there are new programs, this thing is called demand side management. So it would be something like when the system, the grid realizes like, okay, I think in 6 hours we're going to be at potentially low renewable generation relative to the demand, I'm going to give a tax credit. I'm going to give some sort of financial incentive for people to reduce their energy consumption during that time. So anything that's a not necessary energy use can be reduced then, and then you can bring the demand back to meet whatever the supply might be during that limited period. And same way, when there's a lot of supply, then you can give incentives for people to move. Yeah, it's smart grid. I'm basically describing the smart grid for you. And one of the kind of key component of smart grid that uses machine learning is this kind of generation scheduling and demand side management. So forecast supply and forecast demand. Okay. Detecting greenhouse gas emissions. So this is a kind of a cool application, I thought. So a lot of work now on just being able to detect using different kinds of imagery where greenhouse gases are, right? So what these cameras, these pictures are showing they're showing the emission of methane, right? So methane is a very potent greenhouse gas. So there are now people who will kind of use these kind of hyperspectral cameras. There's also now recently, they're launching satellites which have sensors that are able to detect different kinds of greenhouse gases. So through these kinds of sensors, then people are going to be able to better manage kind of where should you be, like where are the sources of carbon in the first place, and how should we be trying to limit them, right? It's a very useful way, it's a kind of a situational awareness for carbon. Yeah, it's also very useful for seeing if people start making progress, you can actually measure that progress in a very quantitative way. Okay, another application, reducing transportation demand. So we talked a little bit about traffic earlier. Now let's think more specifically around shipping and around personal driving. So shipping examples. Oh, someone can't connect. Yeah, let me know if you can't hear. Okay, so the shipping example is just you want to be able to measure how much truck traffic there is on roads. Right? It's a very basic problem. It's like asking how many doctors are there in Nepal. Another question you can ask is how much freight traffic is there along this highway every day? Right? And some countries or some municipalities are able to install sensors in the roads that are able to detect like this weight corresponds to a truck and it's loaded, and this is how much freight is being trafficked through this highway. But then that's a pretty expensive thing to do, right? And you can't put those sort of sensors everywhere. So what this work did instead was they took satellite imagery and then they built a data set of this is where the trucks are, right? And then they're able to then, oh, is there a question?
Okay, Martha, I can see you raising your hand. Kindly ask your question in the chat window. Okay, I don't know if you can hear me, but please use the chat window. Kris, we can go on with that. We'll answer questions from the chat window.
All right, yeah, sorry. Yeah, I'm getting distracted with this, even just this one story. Okay. The point is you're able to build an object detector. You're able to build an object detector that's able to recognize the trucks. And then from there, you're able to get pretty accurate estimates of this is the amount of freight shipping along different roads. And then that can guide high-level decision-making, right? So if you want to try to figure out how to reduce the amount of truck traffic, then it's helpful to know where the truck traffic is. Okay. Another example I like is they were trying to understand what makes people use public transportation. Right? Because if people are able to switch transportation modes from personal cars to public transit, that would also increase the efficiency or that would increase energy efficiency. And you can use the same kinds of technology as before. So this study, what they were using is they were looking at the cards that people have for getting onto the public transit. And they were looking at their mobile phone call detail records. So the point is, once you know what kinds of public transit ridership gets a lot of, or what kinds of programs increase public transit ridership, or if you can figure out where are the areas of highest congestion, then you're able to then plan out new lines that will maximize ridership down the road. So again, it's a systems problem. You don't necessarily need to invent a new car or a new kind of public transportation, but you need to implement it and design it in a very efficient way. Okay, another example around efficiency in buildings and cities. So kind of first, think about individual building level, right? So you saw in the earlier slide with all the different sources of greenhouse gas emissions, some of the main sources are around, heating, right? Heating for buildings, heating and cooling too, actually. So how do you make a building more efficient? Well, the way that heating and cooling works right now is basically an optimization problem. It's a control problem, right? You are trying to control the temperature under some constraint around what the comfort level is, right? So you don't want it to be too hot, you don't want it to be too cold. But then you simultaneously need to meet that constraint while minimizing some sort of energy objective. You want to consume as little energy as possible while doing this heating and cooling process. And you can imagine if you use contextual information, if you know what the weather is like or is going to be like, if you know about the flow of heat through this building, then you might be able to build a control system that's kind of reacting in a very fine-grained way, right? So that's what smart buildings are around. So as you try to build a control system that is kind of very finely adapted to the needs of that environment, but also reducing the energy consumption. So kind of a point here is you can have it respond to the energy grid, right? So if you have a smart building connected to the smart grid, then when there's like a peak in renewable energy supply, then you can make sure to do most of your heating or cooling then, versus when it's less supply. So this is an area that's actually been picking up quite rapidly recently. I've just in the last couple months, I've seen a whole bunch of new data sets getting released and review papers being released around building efficiency. So feel free to ask about this later. So that's at the kind of microcosm, small scale. At the macro scale, machine learning is also very useful for gathering infrastructure, right? Or information about the kinds of buildings that are currently out there, right? So smart building is thinking about how do you make one building efficient? You can also try to map out all the buildings in some city or some country, even these days. Using LiDAR, you can use street view, you can use satellites, and you can try to see are there buildings that are in need of retrofit, right? How many buildings are in need of retrofit? Is there a way that we can kind of target particular municipalities for our campaigns to improve these kind of retrofitting in a way that once it's retrofit, then it will be much more efficient, right? So generating that kind of policy level data is something that machine learning can support. Yeah, I've seen examples where there is no centralized database of solar panels, right? It's not like every solar panel has to get registered with some authority in the government. Like that doesn't happen, right? But what you can do is you can take images but these areas, there seems to be an absence. Right? So maybe we should direct our campaign to improve the solar use at that neighborhood. Okay, public health. So this is, I think sometimes people are surprised to hear that climate change is so deeply entangled with public health, but it really is. There are many ways that climate change will affect people's health. The main ways are there's going to be a lot more extreme heat waves, and extreme heat can, especially for vulnerable populations, it can exacerbate underlying health conditions, right? Also, there's going to be decreasing air quality and vector-borne diseases. So diseases carried by mosquitoes. This is going to be, the ranges of those kind of pests or vectors is going to be increasing as kind of more areas become tropical. Machine learning can help in these sort of things too, right? So the examples here is you can try to analyze where are mosquitoes going, right? Or have their habitats expanded. And you can try to monitor that for disease surveillance. And you can measure disease exposure, right? So measuring excess mortality from heat waves, this is something that people can quantify. Okay, and then final point here, personal energy use. So machine learning can help a lot with understanding personal carbon footprints, right? So there are now several apps around being able to compare different consumer choices, right? So, the ideal thing is naturally like just consume less or like don't fly, things like this. But then if you are going to consume something, it's nice to know what is the carbon footprint, right? And then that requires knowledge of kind of the whole life cycle of a product, right? And that's kind of knowledge that would require, a trip to the library every time you wanted to make a decision. But if you can, take all that pieces of information and compress it down to something that's a little bit more digestible, then you might be able to figure out what's the more efficient option. Okay, agriculture. So this is one of these kind of surprising things where agriculture could be net carbon negative, right? Plants absorb carbon. So you would think that it would be possible to make an agricultural system that's net carbon negative. But right now it's not. Right now it contributes to greenhouse gases. The reason is because the current farming practices is basically like, you till the soil is like you're flipping the ground around, right? This releases a lot of carbon. Because it's such a broad, not a very precision process, right? So what machine learning is being used for now more and more is it can allow some sort of like precision agriculture, right? So you can look at the heterogeneous environment for some farm and you're able to say like, okay, these are the kinds of crops that you should be using for the different parts. These are the different kinds of amount of water needed in different parts, right? So that's agriculture, but also forestry. So forestry has emerged as one of these kind of main areas that machine learning is being used for climate change. The idea is that by growing forests or by preventing deforestation, then you can then that helps a lot with absorbing carbon. Or, deforestation releases a lot of carbon into the atmosphere because these trees have been storing carbon for a long time. This can be done using all sorts of technology, right? So here's example, they're using satellite image to figure out areas that have been deforested, this image on the left. So loss of tree canopy. I've seen other applications where they're able to not just say that this is an area that has experienced deforestation, they're able to say why it got deforested, right? So you might be able to recognize from an image that this is deforestation due to wildfire, for example, or deforestation due to production of some kind of commercial crop, right? There are also examples where people now have, they'll use audio of the forest and be able to detect illegal logging, right? Things like this. But in general, anything that can be done to preserve rainforests or forests in general, that is very good for climate change. Okay, and supply chain management, right? This is another one of these things that happens behind the scenes, so you might not think of it as very relevant to climate change. But then when you look at the sources, like why is there so much shipping, things like this, then you can start seeing where the source of carbon comes from and what can be done to try to optimize it. So I think that whole concept of supply chain management is easiest to understand through a kind of funny example. So this news article on the bottom right, 12,000-mile trip to have seafood shelled. So what happened was these fishermen in England, they were getting shrimp, right? They were harvesting these shrimp. And then to deshell them, you have to take off the shell from these shrimp before you can sell them in the supermarket. And then to deshell them, they flew them to Thailand because that's where the labor cost was the lowest. And then they flew it back to England to put it in the grocery stores, right? And flying is a very expensive thing from a carbon point of view. So this just comes across as like the most absurd process of like populating a supermarket, right? But it was the most economically efficient, right? It was terrible from a carbon efficiency point of view, but economically it was efficient, right? So the point here is like, in the same way that people can use technology to optimize economic efficiency, that same kind of technology can be used to optimize carbon efficiency, right? So if these logistical supply chains were planned with carbon efficiency in mind, that could have a very substantial impact on climate change. Okay, so those were kind of domain-based examples. I'm going to talk now about some machine learning examples. So this is kind of the previous, if there's certain domains that you're interested in, like if you're interested in transportation, if you're interested in forestry, those were some ways that machine learning can help. Now, if you are interested in, forecasting or text models or anything like this, I'm going to talk about some applications to climate change. Okay. I don't know much about blockchain, but yeah, I think it would be an interesting discussion to have in the doc. So computer vision. So how can computer vision help? So one general way is it can help with annotation for found imagery. Right? So I already mentioned a few things around satellite imagery. Here's the example with solar panels, actually. So you can see here is different counties in California, and then the color in each cell, the amount of purple is how much solar panel is there in that neighborhood, or that, I think it's census tract even. And the way that they were able to build that map, which is very relevant for policy decision making, is they were able to look at the satellite images and recognize, okay, there's 22 meter square solar there. There's 148 meter square for solar panel there, right? And this is just you can build a detector that can find that and then compute these totals, right? So that's one kind of way computer vision helps, right? Is existing data sets, try to analyze them. Another way computer vision can help is you deliberately introduce certain kinds of sensors, right? So on the example on the right, they've put in these kind of cameras in order to observe the birds, right? And then you can count the amount of birds and the different types of birds. So this is useful for ecosystem monitoring, right? It can create a little bit more data-driven and targeted conservation. Okay, text data. So this is these things. None of the examples I've really talked about so far have much NLP, but there's actually quite a bit of work that could be done using NLP for climate change. So one example is summarizing big literature areas. So I've seen a few examples of this now, both in materials science. So material science, you want to build better batteries, but there's a whole bunch of literature on building better batteries. How do you figure out the most promising new material? One answer is mine the literature, figure out the most promising chemical combinations, right? Or even in climate change. So usually whenever you hear about climate change in the news, it's often the International Panel on Climate Change has released some new report. It has the findings from scientists from all around the world, right? And what IPCC is often doing is it's just doing this kind of very comprehensive literature reviews across everything that is known about discussed in climate change. I wish I could zoom in more. But yeah, you can see like the top left little cluster this is everything that's being studied around climate change and glaciers, right? Kind of the bottom, there's this green cluster around disease. There's a cluster around water and energy, right? So this is kind of all the papers, each point is a paper, right? And you can now see how is the attention of the climate change research community shifting over time? Are there areas that are understudied? Are there areas that we should be supporting more researchers? Okay, so that's this kind of first general application for NLP. Second kind of application is you can try to annotate data in a way that will augment people's work, right? So all sorts of found text data. So here, this picture is their tweets that were after Hurricane Sandy, right? And you can start seeing certain themes emerge. So yeah, what they were able to do eventually is able to take different tweets and say like, okay, here are the tweets about caution. Here are the tweets that are giving raw information like photos and videos. Here are the tweets that are reporting missing people, right? This would be a really time-consuming thing to do, just to like go through all the Twitter feeds around the hurricane. And it's not a good use of the emergency responders' time. But if you're able to quickly isolate the most important tweets, or at least if you're able to count, here are the different types of tweets. Areas of a wind farm that might be about to break down is helpful to know in advance, right? Also, things like, knowing drought risk, right? If you're able to tell even just a couple months earlier than would be known now, or even a few weeks earlier than would known now, then you can start planning like, okay, let's disseminate extra food supplies there so that you can preempt the food security problems before they even start, right? Okay, so that's like real-time resource allocation questions, right? So the information coming in right now, and you need to make decisions on the order of days to weeks. Right? There's also kind of long-term forecasting problems. This is also very commonly used in climate change literature. So examples are around transportation demand and climate systems. So transportation demand is, you might want to say, this is how we've been rolling out electric cars so far in this country. I want to try a mix of these different programs. So let's say I install an energy or a battery charging station every 150 miles, and I give this sort of tax incentive. How many people do you think will buy electric cars or like switch to electric cars, right? That's a kind of question that you can start to get at using forecasting techniques. You can look at a whole bunch of other countries. You can see how they deployed electric vehicles and how their different kind of government policies affected the way it was adopted. And then you can start saying like, okay, this is how many people we think will be using electric cars. Okay, yeah, we're almost done. And then, yeah, also in terms of just overall climate change, right? So everyone talks about being able to forecast temperature, and that is one of the major applications. But there are a lot of other kind of climate properties that are interesting to know. So here's cryosphere properties. So it's the amount of ice in different places. So if you want to go one step beyond what will be the temperature, you might want to know how will that change in temperature affect precipitation? Or how will it affect ice, right? Or water supply, right? Then it's useful to have all these kind of long-term forecasting. Okay, reinforcement learning and control. So we already talked about buildings as a control system. So buildings are one of these kind of key areas where reinforcement learning can help. I'm showing two new examples. So the one on the bottom left, this is the example of using RL to improve the efficiency of a data center. Right, so data centers are, this is where all the work of the internet is being done, right? They're these big buildings in often like very cold places, right? So that they don't have to pay so much for cooling, right? But then, yeah, they will, instead of having kind of typical control strategy that people have been using for a long time for these data centers, if you're able to adapt it to machine learning, then it can get that much more efficient, right? It's picking up on very subtle signals. I think I remember someone saying like this data efficiency from Google, the way it was figuring out improvements were around things like it realized that people were going to be on YouTube more at a particular time. So it made sure to kind of crank up that part of the data center around YouTube and reduce in other places, right? So these are very subtle signals that would be hard for just the overall data compute environment to realize. And the example on the right, this is a natural environment. So this is trying to figure out when to allow controlled burns in national forests. So the idea is like a controlled burn can prevent a very large wildfire later on. But knowing when to do a controlled burn is a really complicated question, right? You don't want to burn unnecessarily either, right? So what this paper was doing, it was using reinforcement learning to try to minimize the long-term amount of burned forest by having smart decisions around burn events. Okay, unsupervised and transfer learning. So this is especially common in climate change applications, right? Because a lot of the things that we are interested in require some sort of expert annotation, right? And expert annotation is expensive. It's not like YouTube, right? Where people just interacting with the app creates labels, right? It's not like we have a count of likes and dislikes for the forest, right? So there's a lot of unlabeled data out there. If you can build better representations of that unlabeled data that helps you in the tasks that you care about, that can have a big impact on all sorts of climate change applications. So here's some examples of satellite imagery, and on the right, it's also about a material design. Okay, I'll talk about some of my personal projects, but we'll go relatively quickly here. So this question, I worked last year on a project around cloud emulation. This is a project at Mila. The question is basically, how will clouds change as a function of climate change, right? This is a major issue in climate modeling because if there are more clouds or less clouds, that affects a lot how heat is trapped or reflected, right? So depending on the type of cloud and kind of where in the atmosphere it is, that's going to affect either heating or reflection of heat. Okay, so how is it done traditionally? It's done using traditional kind of climate model, right? But the idea here was we can try to use like a generative model, right? Trained on existing examples of here is weather context, like here is the humidity and the temperature and the precipitation. And then given this sort of background, you can try to produce an image that looks like the clouds that we would expect, right? And this is a conditional GAN, basically. And then using this, you can kind of approximate the result from a traditional climate simulation. And yeah, the hope is this can eventually, once we have a good enough emulator, then you don't need to use these very expensive, like computationally intensive climate simulators, or you can at least supplement them. Yeah, don't worry. My email is on the first slide and you have access to the slide. Okay, so yeah, here are some examples of real and simulated images, right? So all that is being given here are the background temperature and humidity and precipitation, right? And it's able to figure out like, okay, these are certain cloud systems. If you pay close attention, you can notice that the texture isn't quite right. Like we're not picking up on the details that are present in the real images, but it's getting close, right? So you're able to tell certain kinds of clouds. Okay, so that was a question at the global scale. You can ask the same kind of question at a local scale, right? So kind of the interesting question at a local scale is there are many different cloud types, right? So you want to be able to say, you know, we have these kind of overcast clouds versus we have these high atmosphere clouds, and you want to be able to detect the different types. Okay, and another project, this is one I'm continuing lately. This is around glacier mapping in the Hindu Kush Himalaya region. So the Himalaya, they're actually the third, they're sometimes called the third pole of the world. The two poles are North Pole and South Pole, that has a lot of ice, but the third pole is in the mountains of the Himalaya. And these have the most ice and the most glaciers besides those two poles. And they're very important for the ecosystem and the livelihoods of people in this region, right? They're a major source of fresh water. Also, if there's kind of a drop in, yeah, they're a major source of fresh water. If there is a drop in the amount of glacier, or if they melt, that can pose big environmental risks as well, right? So glacial lake bursts happen and they can have pretty bad effects on villages downstream. Okay, so here's a picture of some satellite images coming from this region, and you can overlay. These are different types of glaciers that you have, right? So kind of these long streams of things. These are debris glaciers, and then these kind of white peaks. These are ice glaciers. And the question is basically, these annotations, the red and the purple, these were created by kind of experts at this mountain and climate monitoring institute, right? It's a very time-consuming process to build these kind of labels. As I'm guessing you can probably already tell, this is just one tiny area of the HKH. So can you at least augment these experts' abilities to create these maps? Okay, and here are some initial results that we have. The work is going to be public already at the Climate Change AI workshop. So we're going to be presenting this there. It's all virtual, so it's actually pretty easy to access. Yeah, and just here are two images of the same kind of little glacier region. The thing on the right, this is the true label. We try a few different models and we try a few different type of prediction masks. Kind of takeaway here was one of the models is just not even able to recognize that there is this debris glacier in the top right. The other models are able to recognize somewhat, but yeah, there's definitely a lot of room for improvement here. Okay, one point. So I mentioned throughout this talk how important it is to have human guidance, right? Or kind of human augmentation, right? So the point here is that we're building also like a web tool around the machine learning so that kind of people can see the predictions as they click on areas, right? And not only they can see the predictions, they can make corrections to the predictions, and that lets the system actually learn from examples, right? That is, I think, the most important difference between machine learning for this problem and just traditional computer vision for this problem. Because looking at these images, you can tell that there are certain areas that are glacier or not just using traditional like clustering sort of techniques. But then you would have to redo it and recorrect it every single time. Versus in machine learning, if you can kind of cluster initially, and then you get a guess, and then a human is able to interact with the predictions and able to mark the mistakes or mark the missing glaciers, then the system will improve. And that's kind of our key idea. Okay, so just recap. We're basically at the end of the session. Recap about climate change specifically. There are a few themes that come up a lot. So one is speeding up experimentation. Right? So if you want to make a better battery, you want to use new materials, you want to improve nuclear power, that's accelerated experimentation. Remote sensing, a lot of the examples that we were looking at had something to do with satellite imagery. Improving efficiency, right? So the point is you don't necessarily need to change anything fundamental, but you need to change the overall efficiency of some system. That's something machine learning can help. Approximating simulations. So there are a few examples earlier where if you have something really time intensive, you might be able to build a generative model that approximates it. And finally, it's important to have some sort of interpretability in a lot of these applications, right? These are not systems that live in a vacuum or on some server with humans never interacting with them. They are often very key for people in decision-making roles. Okay, a cautionary note. So first, problems that seem really cool on paper might not actually be impactful, right? So favorite example of this is kind of this middle image here. This is a picture of an area which is emitting methane. It's a picture of a methane leak. This does not seem like a cool problem at first until you realize that methane is such a potent greenhouse gas and that if you were able to detect and stop all the methane leaks, that would have a kind of very huge carbon mitigation potential, right? So it doesn't sound as cool at first, but it's very impactful. There's something called the Jevons paradox, which is important to be aware of, right? When you make something efficient, that doesn't necessarily lead to decarbonization. Sometimes making things efficient leads to more consumption, right? Use carbon in the atmosphere, then this can really help. If your intent is purely to make things more efficient, that might not have the intended consequence. And the last point, work with domain experts, right? People have been working on climate change for a long time now. There are all sorts of communities, from energy to forestry to transportation to buildings that have been working on improving the efficiency of these systems from a carbon point of view for a very long time. Find these people, think about the kind of decisions that they have to make, analyze the tasks that they work on, and see if you can streamline some part of their workflow. See if you can augment them. The point is not to come up with a machine learning algorithm that will solve climate change. Like, the point is to play your role in this wider societal mobilization against it. Okay, what can you do, right? 4 things. 1, learn, right? Learn different skills that are relevant at this intersection climate change and machine learning. So we have a paper on just surveying different applications. That's where a lot of these examples I gave come from. Collaborate, right? So it can be hard to find a collaborator at first. I remember when I first started trying to build collaborations with people, I would first analyze public data, right? Like people don't want to have a meeting with you if they think they're going to waste your time, right? But then if you have a portfolio where you show that you've understood the domain, at least using some public data set, and that you can already speak the language, you've already written a little report, right? Then people will take you much more seriously, right? And you'll actually be able to do better in the collaboration as well, right? Okay, next point, make sure to listen, right? Don't dictate what you think the collaborators need. Actually observe them in action. Observe how they work, and then try to see whether there's anything that you could build that might actually have a chance of being adopted, right? And that's kind of the final point. Make sure your tools are adopted and deployed, right? Having a whole bunch of pilot projects is not going to fix climate change. Okay, yeah, some more final tips about collaboration, right? Reach out to people you find interesting. It was through a lot of these kind of consulting, like volunteer consulting, right? And working with people on practical problems. That's where I've learned much more than I ever learned in, well, I've learned a lot in my classes too, but I learned just as much, I think, from working on real projects with people. Yeah, build a portfolio, I mentioned this before, and acknowledge that you will be a novice, and that is okay. You can, like, don't pretend that you will be an expert at a collaboration from day one. Figure out what manuals they use, see if they have any training programs that they went through themselves, attend meetups on the topic, learn how that area works. Okay, and see if you can transfer your knowledge, right? Building a machine learning tool that kind of exists and then is kind of the thing that the data scientist kid made, that's not useful, right? That is something that will last for a few months, but then can't really have an impact in the long run, right? The way that you can transfer your knowledge to people with domain expertise, I think build packages just so that people know how things are working. We're holding another one in December, and it's all going to be virtual. Okay, thank you so much. I think if we have time, we can go back to the Google Docs. I'm also happy to answer. I noticed that there are a few questions in the slides, but thank you all for your attention.
Okay, thank you, Kris. The participants, we've had a great time listening to you. Can you check the chat window? There are a few questions for you. For the person asking if we are going to share the content of this video, yes, every attendee will have access to all the videos of this bootcamp at the end. So, so you have access to this. So, Kris, we have some questions in the chat window. If you have answers to them or recommendation, you can let them know. Okay. We have a few more minutes. So there was a question about, okay, so we have the general announcement that we have less than 10 minutes to go. So Kris, we can go to the Google Doc if we can discuss some of the points there. And then there's a question from Alabi. Alabi is asking, hello, Kris. Most of the approach of AI for social good is about carbon control. Why is it that? And can you talk more about what you meant by carbon impact of footprint? Kris, did you get the question?
Yeah, I hear the question.
Okay.
No, it's a good question. I think it goes back to there was it goes back to kind of why do we care about carbon in the atmosphere in the first place, right? And it's all based around the greenhouse effect, right? So it's just like when you go into a greenhouse, like a physical, actual greenhouse, right? The way that the windows are set up, it will raise the temperature of the room compared to the outside environment, right? So like I could go to a greenhouse in Montreal in February where it's usually like minus 15 degrees outside. But then everything would still be warm in the greenhouse, right? And there wouldn't even be that much heating, right? So that is kind of what carbon does, right? Carbon kind of acts like that sort of special window that raises the temperature of everything below it. But this causes a lot of problems when it's the whole planet and not just some building, right? So it's kind of people will talk about the atmospheric carbon level, right? And that is what ultimately affects the temperature on the planet and has all these kind of downstream climate effects.
Okay.
Yeah, carbon impact and carbon footprint. Yeah, it's basically what does each individual contribute to that.
Okay, so Ibrahim is asking, can we use AI in geoengineering to curve GHG?
You can. I didn't get into this at all. It's a little bit of a controversial topic. But there is a section in our paper, the Tackling Climate Change with Machine Learning paper, that is specifically about solar geoengineering. Yep. So yeah, I'm not an expert in it, but I recommend you check out that section.
Okay. Okay, so Kris, we have about 5 minutes to go. I would like almost everyone to join the room back. So if you have some feedback on the Google Sheet that the team collaborated on, I think you can take that in the next 5 minutes if you would like to. Okay, hi Kris. Okay, hello Kris, can you hear me?
I can hear.
Yeah, okay. Okay, I'm back on. Can you hear me, Kris?
Yep, I can hear you.
Okay, so we've come to the end of this session. We're about to go back to the main room. Thank you everyone for participating, for answering questions, for putting your questions in the chat window. My name is Wura Olaoyewusi. I've been the co-host of this session. Thanks again, Kris, for being part of this. I hope you had a great time too.
I really enjoyed it, and everyone enjoy the rest of the bootcamp.
Yeah. Okay. So please, you can leave. When you click on leave, it gives you an option to go back to the main event. So kindly click on that. For everyone, again, asking for a link to the session, the videos. For every bona fide bootcamp attendee, you will have access to the content. Yes, Kris, there are a lot of thank you messages. Yeah.
Yeah, I appreciate it. It's nothing.
Okay.
Take care.
Okay, bye. So please join the main room. Click on leave room, and then you can go to the main event. Leave breakout room. That's what you click on. Okay, please go to the main event. Leave breakout room. That's where you click. Okay, I think I can confidently leave now. Let me see the number of participants that.